All right, welcome back. Let's go ahead and take a look at some calculations using Ksp and how it's related to solubility. So in a previous lesson, I kind of talked about what Ksp was, and I showed you how Ksp and solubility are connected together, and I was telling you that they are not exactly the same thing, that there is a slight difference between the two, but they're kind of related. So here's how we're going to do this. We're going to look at calculating the solubility of barium phosphate. Okay, and the Ksp is given. It's 6.03 times 10 to the minus 39. We're going to calculate this in moles per liter, which is the molarity. So we're going to actually calculate the molarity of barium phosphate, how much of this will dissolve in 1 liter. Now, my first thing I'm looking at right away is at the fact that this Ksp is so low. Since it's to the negative 39, this is not very soluble. Okay, it's not soluble. So it will dissolve to a small extent. Okay, oops, I spelled that correctly. Okay, it's not soluble. Well, I should say not very soluble. Okay, so it will dissolve, but just to a small extent. So let's see if we can calculate that. First thing we're going to do is we're going to go ahead and start with, since we're dealing with equilibrium, and I know we're in equilibrium. Well, this problem should say calculate solubility of a saturated solution, so I'm going to assume that it's saturated, and I probably should have wrote that in the problem, but we're going to go with a saturated solution of this, okay, this barium sulfate, or I'm sorry, barium phosphate. So we start with the equilibrium expression, so barium phosphate to here, that's the solid, and that's going to go to equilibrium because we're assuming it's at saturation. Okay, so there's our equilibrium, or at least our equation. So let's go ahead and put in the ice table. So anytime we deal with equilibrium, it's a good idea to use the ice table. So in the beginning, I don't have any barium ions in solution because it's all the solid. Then I drop the solid into the solution, and the dissolving occurs. So I'm going to get 3x plus 2x. I'm going to follow the same rules that we did when we dealt with equilibrium earlier. So all the rules still apply. One thing that students tend to make mistakes on is they forget about the 3's and the 2's here in the coefficients. So remember that when we deal with coefficients, we got to bring our 3 down, and we have to write the equilibrium expression. We have to make sure that we include that those numbers. So let me show you what I'm talking about. So if I do the Ksp equals, I'm going to write the barium ion. Remember, we take the concentration of the ions and we take them to the power of the coefficient. So I got to remember to bring that 3 here and here. So there's 2 places I want to bring that 3. Okay, so don't forget that. Same thing with the 2 in the coefficients there. So I'm going to do barium phosphate, and I'm going to take that to the 2nd power. Now, what I'm trying to figure out, okay, since this is the background, or should say the backbone of our equilibrium, what we're trying to figure out is how much of this solid is going to dissolve. How much of the solid can I get in the solution and dissolve into the ions? So this is really what I'm looking for here, is I want to figure out, this is the number of ions that can be in solution, right? These here, these 2 values are the concentrations of the ions when we get to equilibrium. So I want to backtrack and figure out how much of this I start with. Now, we don't really look at solids in equilibrium, but remember what we're figuring out here is how much of this is actually going into the dissolving and breaking down into those ions. So, you know, it's a little confusing, but we really don't care so much about the solid, but we do because we want the amount of solid that's going to dissolve. Okay, so my point is, if I put X here, right? If this is the amount of X that I put in, this amount of X, whatever this barium phosphate is, 3 of them will turn into ions of barium, and then I'll get 2 ions of phosphate. So really what I'm looking for in a lot of these problems is I'm trying to find X, because X is almost always going to be the solubility of the substance I'm looking for. Okay, so it's usually I want to find X. 99% of the time when I'm trying to find solubility, I want to solve for X. So I know what the Ksp is, so I can come over here and I can substitute X, because it's 3X, because I will get 3 times the solubility of, you know, the barium ions are 3 times the solubility of the original substance. Then I can take over here the phosphate, take that to the 2nd power, and again, don't forget the numbers here, the 3's and the 3's and the 2's and the 2's. That is probably the most missed part about these questions. So I'm going to go ahead and simplify. So 27x to the 3rd, that would be what I get here. And believe it or not, a lot of students take the 3 and the 3 and they write 9 here. I see that quite a bit. 3 to the third power is 27, not 9. Then I got 4x squared, and I can continue and just bring everything together, and I have 108 x to the fifth. So now I have my KSP, which is equal to 108 x to the fifth power when I put all that together, which is equal to 6.0 times 10 to the minus 39. Again, a very low KSP, which means my reaction heavily favors the solid, so I'm not going to get many ions, but I will get some. And if I do the simplification here, I can go ahead and solve for x. My x is going to come out to be equal to 8.9 times 10 to the minus 9 molar. And that would be the solubility. So this is the answer that I'm looking for. So this is the solubility of barium phosphate. So if I make a solution with this molarity, I'm going to expect this, this many ions in the concentration. And I can figure that out. I could figure out how many ions are in solution at this point because I know how much of this is dissolving in the solution. And that's how KSP and solubilities are connected together. The KSP is just giving us an indication as to what degree the reaction favors the products. Okay, and obviously the bigger that number, the more ions I'm going to get in solution. So if I wanted to figure out the barium, I would just take 3 times this number, and then I would get the concentration of barium ions, and then I would do the same thing for my phosphate ions. Okay? All right, so let's take a look at another example. And in this example, what we're doing is we're going to take and calculate the solubility of strontium fluoride in a 0.2 molar solution. Now, in the last one, what I did was I calculated the solubility of the barium phosphate in pure water. Here I don't have pure water. Here I actually have a solution that already contains ions in it. So if I take a look at the setup, what I'm starting with is a beaker, okay, that's going to have in it some solution here, some water. And what I'm going to put into that solution are some sodium ions that are already present in there and fluoride ions. So the solution already contains 0.200 molar sodium fluoride. How does this affect the solubility of strontium fluoride? So if I take strontium fluoride, okay, so I've got the equation set up, and what I'm looking at is the ability for this to dissolve and dissociate into ions. That's what solubility and KSPs are all about. But the problem here is I'm going to start with this fluoride ion already in the solution. Sodium ions I really don't care about because they're spectator ions. It has no effect here. It's not a common ion to the solution that I'm dealing with, or the strontium fluoride I have. So it's just this fluoride ion. So when I start this problem, what I have to do differently here is when I do the ice table, is I have to actually start with, because in the beginning I don't have any strontium, but I do have some of the fluoride ions. I actually have 0.200 molar fluoride ions in the solution. Okay, just be careful here because this is a 1-to-1 ratio, so that sodium fluoride dissociates into sodium ions and fluoride ions. But just watch out, because if this were a 2 here, if this were a positive 2 ion, then I would double the amount of fluoride, and actually it would be 0.4. So just something that might happen in a future problem, so just be careful. Plus X over here, because again this reaction is still shifting to the right to dissolve, plus 2X, and again don't forget the 2 that's in here, because you've got that 2 you got to bring down. So let's make that a little bit more clear. A 2X here because of the 2 here. So when I'm done, this is going to be at 0, or I should say X, because 0 plus X is X, and then here 0.2 plus the 2. Oh, I guess I made a big deal about that 2, and really it kind of dropped out in this particular setup, but that's okay. I'll show you where that's going to come back into play in just a second. Okay, so remember, when we deal with this kind of thing here, because the KSP is so low and the shifting to the right is so marginal, we can actually drop out that 2X, just like we did for any other Ks that were very low. So then I come here and I write out my expression. Okay, so I write the expression out and then I plug the values in. Couple things to note here. A lot of students tend to skip this step, and when they skip this step, they tend to miss the 2 here. They tend to just write x times this and move on. But remember, because of the 2 that's in the balanced equation, I have to put the 2 here. And as a result of that, I also have to make sure that that 2 is in this section here. So a lot of people miss this too. Don't do this. How do you not make this mistake? Because you write out the expression and you put the 2 in here to kind of indicate that it's there. So I'm going to go ahead and continue. Ksp is equal to x plus all this, so it's going to come out to 0.0400 times x, which is equal to the Ksp, which is 7.9 times 10 to the minus 10. Now what I can do is solve for x. And when I solve for x, my value comes out to be 1.98. Oops. Times 10 to the minus 8 molar. So this is the solubility of the strontium fluoride in a 0.2 molar solution of sodium fluoride. Now in pure water, in pure H2O, the solubility of the strontium fluoride is actually going to come out to be 5.8 times 10 to the minus 4. So when we're looking at it in pure water, the solubility is definitely a lot higher than it is when we have it in this solution that already has those ions. So remember, what the common ion does to the solution is it limits the ability for it to shift to the right. It can't shift as far to the right because there's already ions that are in there in solution. It can only shift enough to bring it to equilibrium, and because those ions are already in there, it's going to stop and limit that. So anytime I have common ions in the solutions already, my solubility is always going to decrease. Okay, so I think that's good enough for the calculations. Good luck with everything, and I will see you soon.